Welcome back to design of RCC structures. After watching this video, you will understand 8 important steps in design of RCC columns. In this video, I will also explain how to solve numerical example on RCC circular column. Columns can be square, rectangular or circular in shapes. For design of column, we will need load on column, length of column with end conditions, and grade of concrete and steel. In design of any short column, we have to follow 8 important steps. That is to calculate area of column, calculate effective length of column, check for short column condition, check for minimum eccentricity condition, calculate area of steel in column, decide diameter of lateral ties, decide spacing of lateral ties, or if the helical reinforcement is provided, then decide pitch of helical reinforcement, and then to draw detailing of reinforcement. Step number 1 is to calculate area of column, that is size of column. On page number 71 of IS 456 in clause number 39.3, this formula is given. This formula is applicable for design of square, rectangular or circular column with separate lateral ties as shown in first figure. But if the lateral reinforcement is in the form of helix as shown in figure 2, as per clause number 39.4, we have to multiply right hand side by 1.05. While calculating area of column, we assume 1 to 2% of area of steel. So, we substitute, for example, if you consider 1% of steel, we substitute 1 upon 100 Ag as ASC in this formula and 99 upon 100 Ag as AC, after which we get area of column. After calculating area of column, we decide size of column. Next step is to calculate effective length of column. How to calculate effective length of column is given on page number 94, table 28 of IS 456. Effective length depends on end conditions of column. There are different end conditions given in this table. First three conditions are important, which I have shown here. In this table, we have to read effective length from last column, that is column number 4. For example, if you read first condition, which states that effectively held in position and restrained against rotation at both the ends. Effectively held in position means it cannot displace in any direction, and restrained against rotation means it cannot rotate, which means both ends are fixed. In such condition, we have to take effective length as 0.65 L. Second condition is effectively held in position at both ends, means at both the ends it cannot displace in any direction, but restrained against rotation only at one end, means it is fixed at one end and hinge at other end. In such case, the effective length is 0.8 L. Third condition is effectively held in position at both ends but not restrained against rotation at both the ends. That means both ends are hinged. In this case, effective length is 1 L. 3 is to check for short column condition. Because the procedure is different for design of short column and long column. Long column is also called as slender column. So in this, we check slenderness ratio of column, which is effective length upon least lateral dimension of column. Least lateral dimension of column means shorter side of column. So if this ratio effective length to least lateral dimension of column is less than or equal to 12, then it can be designed as short column. Next step, we check for minimum eccentricity condition. In this, we calculate minimum eccentricity of column and compare it with permissible eccentricity. So we must get E minimum less than or equal to E permissible. If we do not get this check, then we cannot design it as axially loaded column. In such case, we have to design it for axial load plus moment due to eccentricity. So let us understand how to calculate E minimum and E permissible. As per IS 456, there are two criteria to calculate E minimum. First is E min is equal to L by 500 plus D by 30. And second is E minimum is equal to 20 millimeter. Out of this, whichever is more is to be considered as E minimum. Then E permissible is 0.05 D. So, if you want to design this column for axially loaded column, then E minimum must be less than or equal to E permissible. Step number 5 is to calculate area of main steel in column, which is also called as longitudinal steel in column. In step number 1, we have already decided percentage of steel in column. For example, if you decide percentage of steel as 1%, then ASC is equal to 1 upon 100 into actual area of column which is provided. After calculating ASC, we can calculate number of bars which is equal to ASC upon A, where ASC is the area of total steel in column divided by A. A means area of one bar. So first of all, we have to decide the diameter of bar. For longitudinal steel as per IS code, the minimum diameter of bar provided in column is 12 millimeter. So you cannot assume less than 12 millimeter diameter of bar in column. So calculate area of one bar. So number of bars is equal to total area divided by area of one bar. Next step is to decide diameter of lateral ties. This clause is given on page number 49, clause 26.5.3.2. In this clause, it is given that diameter of lateral ties is 1/4 of largest main bar or 6 millimeter, whichever is more. For example, if the diameter of main bar is 20 millimeter, then 1/4 of 20 means 5 millimeter, and second condition is 6 millimeter, whichever is more. That means diameter of bar will be 6 millimeter in this case. So this clause is given on page number 49. There is one printing mistake in IS code. So here instead of 16 millimeter, we have to read it as 6 millimeter. Step number 7 is to decide spacing of lateral ties or pitch of helical reinforcement. The lateral ties can be provided in two different forms. That is, lateral ties provided separately as shown in figure 1 or helically as shown in figure 2. So let us first understand how to decide for first case when the separate lateral ties are provided. So this clause is given on page number 49, 26.5.3.2. So in this clause there are three conditions given. The pitch should be minimum of, first is least lateral dimension, that means the shorter side of the column, 16 times smallest diameter of longitudinal bars or 300 millimeter. Out of these three, whichever is minimum, that we have to provide. Next, let us understand how to decide pitch when the transverse steel is provided in the form of helix as shown in figure 2. The clauses related to this are given on page number 71, clause number 39.4.1. So this is what given in the IS 456. Now let us understand this in more detail. What is meant by pitch of helical reinforcement is shown in top figure. In bottom figure, D means the overall diameter of that column. DC means diameter of core. Diameter of core is equal to diameter of column minus 2 times of cover. In column, minimum cover of 40 millimeter is provided as per IS code. Phi S is diameter of helix. Now in that clause in IS code, this formula is given. Volume of helical reinforcement, ratio of volume of helical reinforcement to volume of core should not be less than 0.36 Ag upon Ac minus 1 FCK upon Fy. Now let us understand what do you mean by volume of helical reinforcement, that is numerator. Volume of helical reinforcement is equal to pi dc minus phi s into as. As is area of that helical reinforcement. dc minus phi s is diameter of helix. Now volume of core, which is in the denominator, is equal to pi by 4 dc square into pitch. dc is diameter of core. So if you substitute equation B and C in equation A, we can calculate pitch using this formula. Now for exam point of view, you have to remember this formula of pitch. After calculating pitch of helical reinforcement from formula, we have to check it for minimum and maximum condition. These conditions are given in IS 456. So in this condition, in this clause, the pitch should not be less than 25 millimeter or pitch should not be greater than 75 millimeter or it should not be greater than 1/6 of diameter of core. So after calculating the pitch from the formula, we have to check it whether it is in between these two extremes. Now the last step is to draw the detailing of reinforcement, in which we have to draw the sectional elevation and sectional plan of the column. Now the steps which we have discussed so far are applicable for all types of RCC axially loaded short column. So these are the 8 important steps to design the axially loaded short column. Now using these steps, let us solve a numerical example on design of axially loaded circular column with helical reinforcement. The data given is diameter of column 400 mm, axial load on column 1500 kN, unsupported length of column is 3 meter, support conditions are effectively held in position at both the ends but not restrained against rotation. That means both ends are hinged, and materials, concrete is M20 concrete and steel is Fe415. Now in this problem, the diameter of column is already given, so it is not required to calculate Ag. We will directly calculate effective length of column from unsupported length and support conditions. Given column, both the ends of columns are hinged and therefore effective length is equal to 1L. So given length is 3 meter, therefore effective length will also be equal to 3 meter. Step is to check whether it is a short column or not. So for that we will calculate the ratio effective length to least lateral dimension of column. So here effective length is 3 meter and diameter of column is 400 millimeter. So if you calculate the ratio, it will be 7.5, which is less than or equal to 12, and therefore it is a short column. Step number 3 is to decide whether we can design this column as axially loaded column. That is, check for minimum eccentricity condition. As per IS code, E mean is equal to L by 500 plus D by 30. L is length of column, which is 3000 millimeter, and D is diameter of column, which is 400 millimeter. If you calculate this, you will get 19.33 millimeter. Second condition is 20 millimeter. Out of this, whichever is more. So out of this 20 millimeter is more, therefore E mean is equal to 20 millimeter. Next is to calculate permissible eccentricity, which is equal to 0.05 D. 0.05 into diameter, that is 400, you will get 20 millimeter. Since E minimum is equal to E permissible, this column can be designed as axially loaded column. In this problem, the diameter of column is already given. But suppose in case it is not given, we can calculate this diameter from the area of column. We can calculate area of column using this formula which is given in the IS code. So if the column is helically reinforced, we have to multiply the right hand side by 1.05. So suppose you consider area of steel as 1%. As I told you that area of steel initially we consider 1 to 2%. If you consider area of steel as 1%, then we can write this formula like this. Multiply right hand side by 1.05. 1% of steel means 99% of concrete. So replace AC by 99% of AG and replace ASC by 1% of AG. So from this formula, only unknown is AG. So we can calculate AG from this formula. PU is the ultimate load, which is the service load multiplied by 1.5. So if you substitute everything in this formula, you will get AG. And we know that area of circular column is pi by 4 d square. So pi by 4 d square is equal to AG. If you calculate, you will get diameter of column. Since diameter of column is given, we can calculate area of steel in column using same formula. So here PU is 1.5 into 1500, which is the load on column. So we get 2250 kilonewton. AC means total area of column minus ASC. So this is the equation for AC, and FCK is 25 and Fy is 415. If you substitute all these in the above equation, only unknown is ASC. So if you calculate, you will get ASC is equal to 3306 millimeter square. Now we have to imagine, or we have to assume, the diameter of bar. Diameter of bar should not be less than 12 millimeter. Here I am assuming diameter of bar is 20 millimeter. So area of one bar is 314 millimeter. So next step is to calculate total number of bars. So using 20 millimeter diameter bar, number of bars is equal to ASC, which is 3306, divided by area of one bar, which is 314. So we get 10.52. So we will round up this to 11. So we will use 11 bars of 20 millimeter diameter. Calculating area of steel, we have to check for percentage of steel, whether this percentage of steel is within the range. The permissible percentage of steel in column is 0.8% to 4%. So ASC provided, we have provided 11 bars of 20 millimeter diameter. So 11 into area of one bar, we get 3454. So from this we can calculate percentage of steel. So we get percentage of steel is equal to 2.75%. So this 2.75 is within the range, means it is more than 0.8 and less than 4%. Therefore, it is okay. This is all about design of main steel. Now next is transverse steel. So here we are providing helical reinforcement. So first we will decide diameter of helical reinforcement. As per this clause, the diameter of helical reinforcement is 1/4 of the largest main bar. Now here we have provided the diameter of bar is 20 millimeter. So 1/4 of 20 is 5 millimeter or 6 millimeter, whichever is more. So out of this 6 millimeter is more. So we will provide diameter of helical reinforcement as 6 millimeter. Next step is to decide the pitch of helical reinforcement. So we will calculate pitch of helical reinforcement using this formula. In this formula, D is diameter of column, that is 400 millimeter. DC is diameter of core, which is 400, minus cover from both the side, which is 40 millimeter and 40 millimeter. You will get 320 millimeter. Then diameter of lateral ties, that is helical reinforcement, is 6 millimeter. So area of helical reinforcement is pi by 4 into 6 square, which is 28 millimeter square. So if you substitute all these in above equation, you will get pitch is equal to 28.4 millimeter. So this is the pitch calculated from the formula. After calculating this, we have to check whether this is within the permissible limit. So let us check for minimum and maximum pitch of helical reinforcement. This is the pitch we have calculated using formula, that is 28.4 millimeter. As per the clause number 26.5.3.2, page number 49 of IS 456, the pitch should not be less than 25 millimeter or 3 times diameter of helical reinforcement, whichever is more. So 25 millimeter or 3 times 6 means 18 millimeter, whichever is more means 25 millimeter. So we cannot provide the pitch less than 25 millimeter. Next condition is pitch should not be more than 75 millimeter or 1/6 of diameter of core, whichever is minimum. So 75 millimeter or 1/6 of 320, which is 53.33, whichever is minimum means 53.33. So minimum limit is 25 millimeter and maximum limit is 53.33 millimeter. So pitch should not be less than 25 millimeter or it should not be more than 53.33 millimeter. Therefore, we will provide helix of diameter 6 millimeter and pitch as 25 millimeter. Now the last step is detailing of reinforcement. So first of all, we will write what are the design details. Diameter of column is 400 millimeter. Main reinforcement 12 bars of 20 millimeter diameter and helical reinforcement 6 millimeter diameter with pitch of 25 millimeter. Now we have to show all these design details on the drawing. It is cover 40 millimeter, transverse reinforcement, that is helix of 6 millimeter diameter with pitch of 25 millimeter, main reinforcement or longitudinal reinforcement 12 bars of 20 millimeter diameter and diameter of column as 400 millimeter. These are the details we have to show in sectional plan. Now in sectional elevation, again we have to show the longitudinal bars, that is 12 bars of 20 millimeter diameter. Pitch we can show in sectional elevation only, that is 25 millimeter, and helix of 6 millimeter diameter with pitch of 25 millimeter as transverse reinforcement. I hope now you will be able to design actually loaded short circular column with helical reinforcement. Thank you.